Okay, let's dive right into this explainer. Today we're unpacking an absolutely massive shift happening in software development right now. I'm talking about the jump from manual AI prompting to this incredible concept called autonomous loop engineering. Honestly, if you're working with AI on a daily basis, this is going to completely flip how you approach your workflow.
So let me ask you something right off the bat. Are you still hand prompting your coding agents? You know what I mean, right? Sitting there typing out a prompt, waiting around for an output, reading it, and then typing the exact next step. If you're basically babysitting your AI turn by turn, you are stuck in the old paradigm. You're actually bottlenecking the entire system with your own typing and reading speed instead of building something truly scalable.
In this quote right here, it perfectly captures where the top minds in the industry are at today. Both Peter Steinberger, who created OpenClaw, and Boris Cherny, the head of Claude Code at Anthropic, are publicly saying, "I no longer prompt my coding agents, I write loops." Think about that. When the exact people building these frontier tools tell us they've stopped hand prompting, well, that's a huge signal that we really need to rethink how we work.
Just think about the contrast here. The old way, that manual prompting, is just a one-to-one turn-based chat. You're the operator manually holding the tool. But the new way, loop engineering, flips that entirely. You're no longer the operator, you are the architect. You're designing a circuit, a recursive, autonomous cycle that literally runs the tool for you. You're building the entire system that hands out the work, checks that work, and decides the next step on its own.
Section 1. The architecture of a loop.
So what exactly is this? To put it clearly, loop engineering means replacing yourself as the prompter. You design an autonomous system to do it for you. It's a structural approach. You define the purpose, and the AI just iterates on its own, utilizing its memory to track what's been done until the job is totally finished. Basically, you're building the environment that feeds the agent instead of spoon-feeding it yourself.
Now, a loop is built on three core mechanical pillars. Think of it kind of like the intake, the processing, and the exhaust of a high-tech engine. First, you've got the trigger. This might be a specific event or just a schedule. Second is the action, where the agent actually reasons and writes the code. And third, the stop condition. This is absolutely crucial. It's the verifiable exit criteria that tells the system, all right, we're done here. Here's the thing. AI is almost never perfect on the first shot, right? It rarely hits 100% success on attempt number one. And that's exactly why a verification engine is so critical. The loop constantly runs this cycle: reason, act, and observe. It makes a plan, implements it, and then checks its own results against your stop condition. If it fails, it observes that failure and just loops right back to try again, all without you having to step in.
Section 2. Execution commands, goals, and schedules.
Let's get into the technical commands used to build these things. Understanding the difference between these two primitives is key. First, we have the /goal command. This is for bounded tasks. You give it a highly objective, verifiable exit criteria, like, say, make sure all tests in this folder pass, and it will just loop until that's true, or until it hits a hard turn limit. Then you've got the /schedule command. This one's for recurring, time-based automations, like running daily pull request summaries every single morning. Basically, use goals for specific outcomes and schedules for automated habits.
But word of warning, you got to be careful here. You can design open loops or closed loops. An open loop is when you just tell the AI, hey, go figure out what to do and do it. Unless you have an infinite budget, that is a terrible idea. It'll result in a massive, endless token burn. What you actually want are closed loops. By setting super objective, done criteria, closed loops give you a highly predictable return on investment for both your time and your tokens.
Section 3. Sub-agent workflows, the maker-checker pattern.
This pattern is brilliant, and it shows exactly why you can't just let one single agent run the whole show. If an agent writes some code and then checks its own code, it is way too forgiving. It's literally grading its own homework. So the maker-checker pattern divides that labor. You have one sub-agent, the maker, that ideates and implements the code. Then a totally separate sub-agent, the checker, which usually runs on a stronger model, reviews that work against strict specs. That separation of duties, that's the secret sauce for strict quality control.
To make this setup even more powerful, we apply a framework called reflection. Instead of just failing and trying some random new approach, the system actually takes its failure data and turns it into verbal feedback. It generates these linguistic reinforcement cues, basically self-reflection, and stores them in its memory. So the next time the agent tries, it's explicitly learning from its past mistakes and getting rapidly better with every single loop.
Section 4. Real-world scale, the Mozilla Firefox case.
423.
Let that sink in. That is the staggering number of real production-level security bugs that the Mozilla team successfully fixed in a single month. And get this, they didn't do it by hand. They did it by building a custom agent loop harness.
To actually pull this off, Mozilla didn't just grab a smarter model. They built a completely custom architecture around it. First, they deployed an LLM judge to score millions of lines of code to figure out where memory safety bugs were most likely hiding. Then, they gave their agents custom tools to actively go out, trigger, and patch those bugs. But the real game changer here is relentless execution. An automated agent will relentlessly try 15, maybe 20 different approaches to trigger a bug, and it never ever suffers the cognitive fatigue that a human engineer would.
Now, how did they stop the AI from just hallucinating fake fixes? They used a crazy strict multi-stage loop. Step 1, the agent literally had to trigger a crash in a fuzzing build, a very objective stop condition. Step 2, a separate verifier sub-agent checked to make sure the bug report was actually real and not just some glitch in the test environment. Only after passing those rigorous automated loops did Step 3 kick in, seamlessly handing that final verified patch off to a real human engineer for review.
Section 5. System Risks. Comprehension Debt. All right, as amazing as all this is, we have to talk about the risks. Specifically, something called comprehension debt. When you've got a loop running overnight, shipping hundreds of lines of code that you didn't personally write, a massive gap starts to open up. Comprehension debt is that rapidly growing gap between the code that actually exists in your system and your own human understanding of how it works. If you're not careful, you'll fall straight into cognitive surrender, basically just blindly accepting whatever output the loop throws your way.
You've got to keep this mantra in your head. Build the loop, but stay the engineer. Human oversight is the absolute anchor for this entire system's return on investment. If you just step back entirely and let comprehension debt take the wheel, your own codebase is going to turn into a complete black box.
Which brings us to a final, kind of provocative thought to wrap up this explainer. Look at your own automated workflows today and ask yourself, are you truly building intelligent loops with clear stop conditions and solid verification? Or, by lacking oversight and human understanding, are you just autonomously scaling your own bugs faster than ever before? Take a hard look at your